Mahantesh sir, has ma'am joined?
Yeah, madam, she is joining actually. That link is not working. It seems I told to rework on that. Just a minute, man. 1 minute.
Okay, okay.
Okay.
A very good morning to one and all present here. Sorry for the delay. Speaker has joined. So I welcome you all for the day two session of FDP on embedded systems and robotics. Speaker for the today's session is Ms. Minimul Thambi, Technical Manager, Wellington Electronics Private Limited. So, introduction to the speaker. She is graduated in electronics and communication engineering. She has done her post graduation in VLSI domain. She has vast experience in embedded hardware with a demonstrated history of working in the research, industrial, embedded control, 8-bit, 16-bit, 32-bit MCU and MPU hardware, architecture, and much more. She has successfully executed electronic product designs ranging from set-top box, OTT STB, digital headends, encoders, ProKits for building automation, and much more. I welcome you, ma'am, for the today's session.
Hi, good morning, Hussein. I'm just trying to figure out this screen sharing. Just give me 2 minutes of time.
Sure, ma'am, sure.
Hi, good morning, everyone. And thank you, Husna, for your introduction. I appreciate that. So, I will be just turning off my video due to this network bandwidth. I hope that is okay.
Okay, ma'am.
Yeah. So you are able to see my screen, right? So in today's topics, I will be covering a corporate overview. It's just a small introduction about our company. Then I will be explaining on the nature of current, then LED circuit design, then it goes to design and development, Basically, I will cover in a product design and development what all we are doing, what steps are involved. Next is about the hardware design flow and the validation stages. So, giving a brief of our company, Velankani Electronics Private Limited, situated in Velankani Tech Park campus in Electronic City, Bangalore. We have in-house latest automated production lines, software and hardware engineers, developers and integration team, production engineers and testers, project managers, quality managers, and HR and admin team. One of our group company is a developer of Indian conditional access system supported by Government of India. I'm just skipping that video because that is about the overall group company. If time permits, I will show you that in the last. So VPL is an integrated designer and manufacturer. So when I say integrated designer and manufacturer, we do here product design on electronics, product design on mechanical also. So once the product is developed, we do in-house product testing and validation, then sourcing, then sourcing means basically the purchasing of components as well as the PCB. We do not fabricate PCB, we just outsource that. After that, we do PCB assembly and testing at our own facility and box assembly and testing. Then comes the marketing, sales, and the after sales product service. So you can see whatever I have mentioned in this green color is what we do in-house. And the certification, of course, we are doing it outside. We are just outsourcing that. And we have an upcoming plan for this chip design, wafer packaging testing, and the product recycle. So this is an overview of our R&D center. Are you able to hear the audio?
No, ma'am. Audio is not it is not audible. We are not unable to hear the audio.
Unable to hear the audio. Okay. Okay, I will just continue with that and I will explain on it. It's just an overview of our R&D center.
Ma'am, video is not getting played. Ma'am, it's not getting played.
Husna?
Video got stuck in between, ma'am. It did not get played.
Oh, video is not playing. Okay.
No.
Now you are able to see my slide?
Yes, ma'am, it's visible.
Okay. So I think there is some issue with the video. I will try to figure it out. Okay, I will just move on to the next slide. Maybe in the last I can show you that a couple of videos. So I hope you are able to see my screen. This slide is the nature of current. Okay, so I will just explain on this flow of electrons. Just to brush up the basics, that's it. So what is actually this current means? Current is the flow of electrons. Suppose if there is a current, electrons are moving, and if there is no current, electrons are not moving. It's that simple. So when we measure the current, we are determining how many electrons are moving. The definition of 1 amp of current is what? It's just 1 coulomb of charge passing by a point in 1 second. Elements that hold the electrons loosely in the valence band, those with a single electron in the valence band, that is called what? Conductors. But on the other hand, elements that hold the electrons very tightly, those whose valence bands are fully occupied, that do not allow the free flow of electrons. Therefore, the opposite of conductors are called insulators. So now here in this animation, you can see there is one atom. So everything including you is made from atom. That is the basic. So here in central location, we have the nucleus. Then we have the proton, neutron, and in the valence band, electrons are there. And you can see the electrons are moving around. So coming on to the next. Coming on to the next slide, it's about the charge field. So we all know that like charge will repel and the opposite charge get to attract. So if electron jumps onto valence band that is already occupied by another electron, it will tend to repel the other electron onward. So here in this figure, you can see electrons travel through a conductor from one nucleus to another. This is how the electrons are flowing, and that's how we are getting the current. So we can picture the charged particle as a sphere. Charged particle radiates the electric field away from it that extends out in all directions. The strength of this field is inversely proportional to the square of distance. So at any time we have two charges separated by a distance, there will be a force field between them. The field weakens as we move farther away from this line. This field is called what? A charge field or an electric field. So why I am explaining this is when we talk about the flow of current, there exists an electric field associated with it, and there comes a magnetic field also, which I will cover in the next slide. Okay, so this is the magnetic field. Here you can see in the picture. When electrons move, that is when the current flows, a magnetic field is generated around the current flow. This is the basis of an electromagnet. Magnetic field is normally oriented in concentric circles. Here you can see the circles around the current flow. So it decreases in strength inversely proportional to the square of distance from the current flow. One thing is it is polarized and its direction can be found out by the right hand rule. So suppose as shown in the picture, suppose if the current is flowing in the direction of that blue line, then if you hold your thumb in the direction of current flow and fingers of your right hand will curl in the direction of field. So when current flows, example on a circuit board trace. So what when I talk about trace, it's just you can imagine that like a cable through a cable we are carrying the current. So trace is a terminology for what we are using for terminology for what we are used in PCB design. So whenever I say a PCB trace, that is similar to a wire carrying a current. So when current flows, both this field, magnetic field and electric field, exist at the same time. Electric fields can radiate not only into space but also to adjacent traces or planes. Magnetic fields circulate around the trace. So just remember this point that whenever a current flows through a conductor, there exists a magnetic as well as electric field associated with it. So electric field radiates and it can also get coupled onto nearby traces. So while designing a PCB, we should make sure that this electromagnetic interference or electromagnetic coupling we are avoiding. Otherwise, some signal distortion will happen in that. So moving on to next. Forces driving current. So how exactly this current flows? Electrons do not flow without a driving force. Some force must move the electrons along from one point to another. So in general, from a practical point, the two categories of force that move electrons, one is voltage between 2 points. And next is the presence of a changing magnetic field that causes electrons to flow. So the major two forces that drives the current, one is the voltage and second one is the changing magnetic field. In case the presence of either of this will cause a current to flow. So here you can see in this animation, it's a copper wire exactly, and the cross section I have a short that. So if we look inside a slice of copper cable, we would see the free electrons of the atoms move from one atom to another. However, this occurs randomly in any direction. So that is just a random movement without any external source or voltage connected. So what is voltage and what is current? Let's see more about that. Let's say there are two terminals separated by a space. Assume one terminal has more charge related to the other. So charge between the terminals is different. Different charges attract each other with a force that is related to the magnitude of charge difference. This force creates electric field between the terminals. So that is about the electric field. The force between these two terminals is defined as voltage. If we connect the two terminals together with a conductor, charge would flow from one terminal to the other. The charge flow is defined as current. In general, current cannot flow without a force pushing it along, which I told previously. If two terminals had exactly the same charge with no force or voltage between them and we connect them together with a conductor, nothing will happen. So always remember there should be a force, a potential difference for that electrons to flow. So in the animation you can see a copper cable is connected to a battery. If the slice of cable were then connected in a closed circuit like what I shown as a source of power such as battery, then the voltage will force the free electrons to move and this will cause them to flow in the same direction. So in the previous slide we have shown that electrons are just moving randomly, but when we applied a force, when we applied a voltage, electrons are flowing in a same direction to try and get back to the other terminal of the battery. So an electric field is a field around an electrically charged object where any other electrically charged object will experience a force. Next is electrical potential difference, or what we say as a voltage. That is the external work needed to bring a charge from one location to another location in electric field. Hope that is clear. That was just about the basics. So voltage, here you can see I have given one battery And in the multimeter, it's showing as 9 volt and connected 3 batteries in series, and it's showing 27 volt. So think of voltage like pressure in a water pipe. When you apply more voltage, it means more pressure. More pressure means more water can flow. So basically, the more voltage means more electron can flow. So that is all about the voltage. Then comes the topic of resistance. So every conductor or every material has got some resistance. Let's see how this resistance is affecting. Resistance is a restriction to the flow of electrons in a circuit. So it will just restrict the flow of electrons. Wires which carry the current will naturally have some resistance. The longer the wire, the greater the resistance. The thicker the wire, the less the resistance. The resistance of flow of electrons is different for each material. The temperature of material will also affect the level of resistance. So the electrical circuit, we all have electrical circuits at our home and everyday use. So there are some specially designed components known as resistors to purposely restrict the flow of electrons. So why we have to restrict this? This is used to protect the electrical components from receiving too much current, and it also can be used to generate light and heat. Maybe in our incandescent light bulb, the principle of that. So resistance occurs when electrons collide with atoms. The number of collisions varies by material. Some materials such as iron will have a very high rate of collisions, whereas other materials such as copper has much fewer collisions. So copper resistance is less. That's why we generally use that as a conductor. So here you can see one LED is connected to a battery and a resistor. So in the circuit where resistor is connected, that reduces the flow of current. In the circuit where LED is directly connected with the battery, too much of current is going into the LED, and LED is just bursting off in that particular animation. Hope that is clear. Next is direction of current flow. How this current is flowing in what direction. So as I said earlier, current is the flow of electrons, and negatively charged electrons would flow from negative to positive. But in general convention, when we analyze circuits or when we do the schematic, we think of current flowing from positive to negative, that exactly opposite of what is happening. So where do these currents exactly flow on circuit board? So here you can see a green color picture, that is a circuit board, printed circuit board. Here you can see some circles and some lines are going here and there. That lines is what we call as a PCB trace. On this trace is what exactly the current is flowing. So PCB trace is nothing but a copper conductor on the PCB that conducts signals on the surface of PCB. It is just a flat, narrow portion of the copper foil that is left behind after etching during that PCB fabrication process. So where do this current flow on circuit board? In almost every case, signal currents on circuit board flow on traces. So that lines are called trace. There are two types of current. One is signal and one is the power. Power is nothing but the power required for the circuit board. So power currents are carried on either traces or plane. Since power needs more current to pass through, we will provide a complete plane of one PCB layer, because then only it can carry that much current. But signal current can be like through a thin trace also it can pass. So when I say a plane, it needs to be large enough to be manufacturable, and it needs to be large enough to carry the required current and small enough to get everything within the desired physical area. Also, when coming on to this power current, it need to be correct length to meet a timing requirement. Actually, that is for signal, and it need to be in a defined size to meet impedance requirement. When I talk about impedance, we always, while designing a PCB, impedance should be controlled. Otherwise, there will be distortion during the propagation of signals. And also, it may need to be routed paired to another differential trace. So differential traces are nothing but two traces, with one trace carries the positive signal and the other trace carries a negative signal, that is both equal to and opposite polarity. That's it. Next is about AC and DC, which you might already know. In AC, the current moves back and forth. So alternating current simply means current flow backwards and forwards in a circuit as the terminals are constantly reversed. So this is, you can imagine just like a tide of the sea. It goes in and out repeatedly. So that is the most common type of electrical power, and which is available in our power sockets of our house. The other type of current is direct current. It simply means that current flow directly in only one direction. That is what we get in our batteries and other adapters, DC current adapters. So another main point is return current. So when we talk about currents, we first started with how a current is generated, the driving force, and where, in what direction the current is flowing. But there is a main topic on the return current. So if a signal is moving from a source, source to destination, I can call it like that way, there will be a return also. Every signal has a return. So in this figure, you can see a forward current is going on to one side, that is on one layer of the PCB. But in the just beneath that layer, you can see a solid ground or power plane, and that's where the return current flow. So control of return current is very important. For one is impedance control, and it's equally important for the EMI. EMI is nothing but electromagnetic interference. And the control of return current is also important for the crosstalk. So what is crosstalk? Crosstalk is nothing but a unintentional electromagnetic coupling between the traces on a printed circuit board. So it basically means the overpowering of one signal in a trace by another the result of this coupling, even though two traces are not in physical contact with each other. So there comes a coupling effect. So also control of return currents is important for controlling the ground bonds. So ground bonds is basically when voltage level of ground reference changes values or bounces to a different value. So ground potential that it is not keeping, that is called ground bonds. So the important point is that we need to make provision for return current. And easiest way to do is provide a proper ground or proper power plane just beneath the signal layer. So universal rule is current follows the path of least impedance. So suppose if we have a AC signal on trace, where is it return current? So answer is it flows on the plane directly under the signal or trace. Why? Because that is the least impedance path. So always whenever you design a PCB, just make sure you are providing a reference plane for any of the signal which you are designing in that PCB. Hope that is clear. So next is about some voltage and current topic only. So you can see two bulbs. To one bulb we have connected a 1.5 voltage of battery, and to the other bulb we have connected a 9-volt battery. So we need a lot of electrons to flow along a circuit and through our lamps to get them shine brightly. So you can see More voltage means more current. So more current means a brighter lamp. But still, how much voltage you can apply? There lies the constraint. The cables and lamp can only handle a certain amount of electrons passing through them. Just like a pipe is rated to handle a certain amount of water passing through it or a certain pressure. What will happen if we exceed? If it exceeds, then this pipe will burst. Likewise, if too many electrons pass through the cable or lamp, then they will burst or burn out. So we refer to the flow of electrons as current, and we measure this in the unit of ampere. Although you will usually hear, okay, some people call it as amps also. So here I have shown one, that is a laptop adapter, charger adapter. And the label also, you can see it here. So laptop chargers tells us that for that particular laptop to work, it needs an input of 100 to 240 volt. 100 to 240 volt, but you can see a symbol also there. That symbol is for AC. So input to the laptop laptop charger should be what? 100 to 240 volt AC. And it has shown 1.5 ampere. So the AC input current requirement is 1.5 amps. And just below that, you can see 19.5 volt. 19.5 volt is the output, which is of DC. And it consumes a current of 3.33 ampere. That is what the manufacturer label says. So input we give as AC, output we give as DC. This output is directly connected to the laptop. So now I guess you might be able to correlate that when you use HP charger onto a Lenovo laptop, maybe it doesn't work. It's because of this specification changes. So you can try to see the labels on your laptop chargers and see to what specification it is designed for, and always try to keep the specification for your any of your electronic appliance to be the same, because the manufacturer has designed that particular device for these parameters only. If you try to match it with some other specification, obviously the appliance will get damaged. Next is I will just give a brief on some points on this circuit design, how to do the design using an LED. So LEDs, as you know, that it is light emitting diode. If we pass a current through one, it produces light. That is the purpose of LED. But what happens if we exceed its voltage and current limit? Obviously, that will get destroyed. So you can see here the LED cross section. LED has a tiny wire inside. This can only handle a certain amount of current passing through it. So how we will determine this current? It will be given in the data sheet. Data sheet of any component we can get from the manufacturer component. So how to connect these LEDs, how to reduce the current to keep LED safe, and how long a battery power the circuit for this LED, those all we can see in the further slides. So LED protection. So here you can see, by the way, the longer lead of LED, that is the positive part, I mean the anode, and the shorter one is the negative cathode. So to protect our LED, we should use a resistor. The resistor is going to make it harder for electrons to pass through. The electrons are going to collide. So you can see a resistor and a copper wire here. So what happens inside a resistor is the electron collisions. Electron collisions, in one way, the energy will be converted to heat. So where to keep this resistor? Should we keep in the negative side or positive side of battery? Actually, the both configurations will work. There is no restriction onto that. But normally we keep the resistor on the positive side of the battery. So why we are able to do like this? Because the function of a resistor is just restrict how many electrons will flow in the series circuit. So here I am giving one example for this resistor. So resistor acts something like a traffic jam. You can see in the figure reducing how many electrons it can flow. Most people will think that resistor is like a speed bump which just slow down the flow of electrons, but that is not correct. Resistor is just, it's not just slowing down. The speed of the electrons will always remains constant, but the main catch here is the number of electrons flowing is what changes. So it's basically reduce the number of electrons flowing through that particular resistor. It's not just slowing down the electron flow. Hope that is clear. Next is how we can, or what value we can use for this LED circuit. The higher the resistor value used, the lower the current will be and the dimmer the LED will shine. So here you can see two circuits. One is of 300 ohm resistor, the other one is of 600 ohms. So when we reduce that resistance, more current is flowing through that, which is of 20 milliamps. That 20 milliamps is typical current consumption of an LED. So LED is glowing bright. On the other hand, when we increase the resistance, when we are when we have implemented using 600 ohms, then current is 10 milliamps, just 10 milliamps only is flowing through the LED, and because of that, LED is dim. So what happens if we, as I told before, there is a positive and negative terminal for this LED. What happens if we reverse the LED? Nothing will happen. It will just simply block the current and the LED will not turn on. Next is, if I am sure you will have this very few basic components in your lab, so you can just try it yourself. I have a LED here, then battery, then multimeter. You can just take any of the red LED or any other LED and 9-volt battery and a resistor of between 360 and 390 ohm, or another set of 3 kilo ohms and 9.1 kilo ohms and a multimeter, and you can connect this positive terminal and negative terminal through a resistor, and we'll see what happens. So here I have used a breadboard. So one is of 360 ohms. You can see LED is more brighter. Then in the other one, LED has become dim because of more resistance which we have used. Okay, so I hope you are able to see this slide of how to use the multimeter. Now take a multimeter, put that into DC voltage mode. Then measure across the far ends of the circuit and we should see around 9 volt. So 9 volt when we measure, that is the voltage of battery. So here how we have measured. So the black probe of the multimeter we have connected to a common terminal, and the red probe we have connected to a voltage terminal of the multimeter, and the black one is going to the negative of battery, and the red wire is going to the positive terminal of the battery. So when we put the probe across the battery, we are getting a 9 volt. That is the battery voltage. Next, voltage drop across the LED. Now let's see what is the across the LED. How much voltage drop is there? So same way, take your red color probe and black color probe and put across the LED. That will show a voltage drop of 2 volt. So 2 volt is there, and when you again measure the voltage drop across a resistor, that will show us what? 7 volt. So out of the total 9 volt, 2 volt is dropped across the LED. So remaining volt, 7 volt, is dropped across the resistor. So the total voltage drop in this particular circuit should be equal to the battery voltage. So the other thing what I want to mention is you might see some variation in the practical scenario. Though the manufacturer has specified that this LED is mentioned for voltage drop of 2 volt, maybe when you connect a multimeter, the actual reading will be 1.9 volt only. That is similar to resistor also. Resistor maybe theoretically it is designed for some 390 ohms, but in actual reading it might be 386 ohms. That is all because of some tolerance. During the manufacturing, we can get closer to the value, but it will not be the exact same value because of that tolerance level change. So always with these manufacturers, they will provide that tolerance level. Tolerance is nothing but that change in values. It can be a 1% tolerance level resistor, or it can be a 5% also. And in current industry, we get a 10-20% also. So it depends on how tighter your constraint be. Depends on that we are selecting the components. So just keep this point in mind. Next is when we talk about LED, this forward voltage is equally important. We can see here at 2 volt. This is a graph of forward voltage versus the forward current, and at 2 volt, what 20 milliampere is there. That is the current consumed when we are providing a 2 volt to this LED. The manufacturer will provide a chart like this, which shows forward current at a given forward voltage. So if we connect a voltage source across the LED terminals and apply a 2 volt, so what we see is 20 milliampere. So what happens if we just apply 1.6 volt? So here you can see in this chart, after 1.5, then middle one is 1.6, then comes 1.7. So if we apply 1.6 volt, there is no current associated with it because that just shows as 0 milliamps. Then if we are applying 1.6 volt, the LED will be off only. So LED will start working if we are providing 1.7 volt only. So that is with this LED. Maybe some other manufacturer will give a different LED which can start from 1.8 volt also. So always when you are taking a component, you have to read the data sheet and you have to figure out what is the minimum voltage for that LED to start illuminating and how much current it takes. That much current also you should be able to provide for that LED to work. Now suppose if you got a LED, how you can test it? So if you have one multimeter and LED, we can test it ourselves. So we can test our LED's minimum opening voltage using a multimeter. if you select the diode mode on your multimeter, so make sure your multimeter is in diode mode, then connect the red LED to the long anode and the black wire to the short cathode of this LED. We should see something like 1.7 volt. That is the typical voltage for the LED. So this minimum voltage is required to turn on this LED. Next is, so most of the standard LEDs are rated for current of 20 milliamps. 20 milliamps, when we convert to ampere, it is just 0.02 amps. So that is the typical value, and we will try to stick on to this for our further circuit definitions. What happens if we go below this? Then LED will become dim only. If we go beyond this, then LED, there are chances that LED will get destroyed. But still, we can go above 20 milliampere, but only thing is, lifespan of the LED will reduce the higher we go. So here you can see in the picture, 7 milliamps, if we are giving very low current, it's not that bright. If we give 19 milliamp near the perfect current, so LED will glow slightly. If we give 21 milliamp, it's slightly too high, so it will bright even more. And while reaching 70 milliamp, the LED will burst. So we should not give that high current to LED. Next, this is a screenshot from manufacturer datasheet where he specifies the forward voltage, typical and maximum. So when typical is 2 volt, okay, it is safe to give 2 volt, but maximum up to 2.5 voltage only. And the forward current is designed for 20 milliamps. So if we give a constant 2 volt and 20 milliamps of current, the LED will glow. But not all LEDs are created equally. This one doesn't reach 20 milliamps. Okay. So that is about the LED, basic LED voltage drop, and make sure you are just referring the data sheet from the manufacturer, and you can test them yourself also using the multimeter. And next we will see some simple LED circuit. So let's say we have a 3 volt supply and we want to connect this to a single LED. So the resistor what we should use is that we know this red wire is 3 volt and the black wire is of 0 volt. So LED will have a voltage drop of 2 volt. So our resistor need to remove the remaining voltage. That means resistor need to drop the remaining voltage. So 3 volt minus 2 volt is what? 1 volt. So drop across the resistor will be 1 volt. And of course the LED, since the LED needs 20 milliamps, using the Ohm's law, R equal to V by I. So resistor value will be 1 volt divided by 0.02 amps. That is 50 ohms. So hope that is clear how to calculate the resistor. Next we have calculated the resistor value. But what power rating it should be? So we will figure out that. LED which has a voltage drop of 2 volt and 20 milliamps current. So the size of resistor, we all give resistor parameter in wattage also. So resistor, the value matters, also the power rating matters. So we have a 9 volt supply in the battery. So 9 volt minus 2 volt, 7 voltage drop for the resistor. Next is 0.02 amps, which comes when we use 9 volt, we will have to select a resistor. So 7 volt divided by 20 milliamps, 0.02 amps, which is equal to 350 ohm resistance. That is our theoretical value, 350 ohms. But there is a problem. 350 ohm is not a standard resistor value. We can have either 330 ohms or 390 ohms. So which resistor value we should select? So as we saw earlier, to ensure the current doesn't exceed 20 milliamps, we need to calculate and see which resistor suits the best. So 330 ohms, when we divide and divide for the current, it will be what, 0.021 amps, and for 390 ohms it will pass 0.018 amps. So for a safer side, since the LED is rated for 20 milliamps, we will just go with 390 ohms. Next is power. How to calculate this power? So power, the formula for power is I square R. Now you know that current, when we use a 390 ohm resistor, that current is 0.018 amps. So power is equal to current square into resistance. So 0.018 square into that resistor value, which is 390 ohms. So the total power is coming to what? 0.126 wattage. So in this case, we can use a 1/4 watt rated resistor. So whenever you just try to search some data sheet of a resistor, there you can see the resistor, then power rating also associated with resistor. So when you select the resistor component, always make sure that falls within the rated wattage. Next is we have covered resistor value, then wattage of the resistor. Next is about the battery. How long the battery will power our circuit? Let's say this battery is rated for 500 milliamp hours. So we can simply divide this by our total circuit current. So how much current is getting consumed in this particular circuit? That is 18 milliamps. So duration, to calculate the duration, we will just divide the battery capacity by the current. So the battery capacity is for 500 milliampere hour, that divided by the current consumption of the circuit, which is of 18 milliamps, and we get the total duration of 27 hours. So this particular circuit worked for 27 hours. After that, battery will be discharged completely. So next is some a sample circuit on this series connection of LEDs. So till now we have seen connecting a single LED. What in case if we want to connect a series of LED, multiple LEDs? So here you can see 1, 2, 3, 4 LEDs are connected in series, and each LED has a voltage drop of 2 volt. So this 2 volt will add together. So 9 volt drop at the first LED minus 2 volt, then second LED again minus 2 volt, then third and fourth again 2 volt each. So remaining what we get is 1 volt. That 1 volt is getting dropped across the resistor. But the current will be same through all these. So 1 volt divided by 0.02 amps, which is equal to 50 ohms. That is the resistor value we should use. But problem with this is, suppose if you want to connect 10 more LEDs, then you should provide that much higher voltage, which is practically not good. So the only solution to this is, instead of connecting the LEDs in series, we should go with a parallel connection. So this is the parallel connection of LED. Here you can see LEDs are connected in parallel, but how to connect the resistors? So two cases are there here. Either you can use a individual resistor in each, for each LED, individual resistor you can use, or you can use a common resistor also. So we'll see both the scenario in further slide. So parallel circuit. Let's say we want to connect 6 LED and two 9-volt battery. Each LED has a voltage drop of 2 volt and each require 20 milliamps. This entire rail is 9 volt. You can see that. The red wire and the black negative terminal is of 0 volt. So each LED will get 9 volt across it. That is, we know that is too much. So we should place a resistor there. And again, to find the resistor value, we should see first voltage drop across the resistor 9 volt minus 2 volt, which is 7 volt, and the resistor value 7 volt divided by the individual current consumption of the LED, which is 0.02 amps, that is 350 ohms. Then we have to find the resistor power reading, which is I square R. So across the resistor 20 milliamps is going, so 0.02 square into 350 ohms, which is equal to 0.14 wattage. So next is total current for this entire circuit. How much it will be? Since each LED is taking 0.02 amps, so that multiplied by 6 number of LEDs. So that is equal to 0.12 amps. So for this particular circuit, we are supplying 9 volt and 0.12 ampere is the current consumption of the circuit. Hope that is clear. Okay, so till now we have just seen a single type of LED. Now what happens if the LED color change? So for different LED, we have different voltage drop. So red LED may be 2 volt voltage drop only, but blue LED is specified for 3.4 voltage and green LED for 3 volt. So let's connect this in parallel and through a 9 volt battery. So the first resistor, I have mentioned it as R1. First resistor voltage drop will be 9 volt and the voltage drop for red LED is 2 volt. So 9 minus 2, which is of 7 volt. And the typical current consumption we will consider here 20 milliamps, 7 volt divided by 0.02 amps, which gives us 350 ohms. So 350 ohms resistor is used for R1. Next, let's calculate for R2. The voltage drop is different. So 9 volt minus 0.4 volt, which is equal to 5.6 volt. So that 5.6 volt divided by 0.02 amps, which gives us 280 ohms. So R2 value will be 280 ohms. Next, come to third resistor. The green LED voltage drop will be 3 volt. So 9 minus 3, which is equal to 6 volt. So 6 volt divided by 0.02 amps, which is equal to 300 ohms. So this is how we should calculate in case if we are using different types of LED. So not always we should commonize the parameters, just check the data sheet and get the voltage drop and calculate for the resistor. And the power wattage the same way as done earlier, which is of I square R. Find out the wattage and see the standard wattage rating available for the resistor. So next is, so till now we have seen individual resistor for each LED. Now this is a common resistor. Common resistor used for this parallel circuit. So total current we have here 3 LEDs. So for 3 LEDs, the total current will be 20 milliamps into 3, which is equal to 60 milliamps. So 60 milliamps must flow through the resistor. Again, for the voltage drop, 9 volt minus 2 volt, which is of 7 volt. So the resistor value what we should use, that is R equal to V by I, 7 volt divided by 0.06 amps, which is equal to 116.6 ohms. So just see what is the standard resistor value available in the market. Choose a closer one to that. Next is resistor power, I square R, 0.06 square into 116.6 ohms, that is equal to 0.49 wattage. That is the resistor power what we need to use. So that covers the some basic circuit design. Next is on to design and development. So how we exactly do this product design, and I will phrase it in that way. So when we design a product, it involves hardware as well as software. So the first block is for the hardware. So before that, we will get the product concept and once the product concept is there, we will do a technical or feasibility analysis whether we can actually implement this concept or not. So that point we will capture into a document called PRD, Product Requirement Document. Once PRD is ready, details everyone. Let's come to this hardware block. We have the board specification. So once the board specification is in hand, the next thing is to start a block diagram, then create a schematic, which will schematic and layout. So schematic, layout, everything I will cover in the upcoming slide. So once the layout is completed, then we have to do the PCB fabrication and then board assembly. So in this activity, we will also start with the mechanical. So when we create a PRD, mechanical specification also will be there. So mechanical engineer will take that and do the drawing and then fabrication, then after mechanical assembly. Once this both hardware and the mechanical is ready, then it goes for a system assembly. So once that is done, what we get is a finished good. So in this hardware activity, we will have the software activity also. So software specification will be there. Then we need to do the operating system stacks, develop the firmware. Then on top of that, development code, then operational code. Then along with the firmware, we need to do the application also. Application layer also will be there. So once after we get the hardware and software, then we need to integrate both and start the testing. So in testing, there will be initial testing, then integration testing, integrating both this hardware and software. Then there will be application or functional testing, whether it meets our particular application that we are testing. Then it goes for environmental testing and regulatory approvals. Once after this entire cycle is completed, then only the product release will happen. So I will just explain further on this hardware design. So as I said earlier, once the concept is defined and once the PRD, that means the product requirement document is ready, we will start with the block diagram. Block diagram of that particular application. Once the block diagram is ready, we will start the schematic. So I have given a picture here with the white background. That is actually the schematic. Schematic is nothing but a logical representation of the circuit. So during the schematic also, we should calculate the power for that particular circuit. So after that, it goes for layout. So you can see the second picture, which shows some red and green traces on that. That is actually the layout. So once the layout is done, the output of layout will be a file called Gerber. So this Gerber file is important because that's what we are giving to a PCB fabricator. So just after that, we will do the component sourcing or component purchasing. So PCBs along with the components, once it is ready, we will do the PCB assembly. So that is the fourth picture. So on the left hand side, you can see a green color board. That is the printed circuit board. So you can see the difference between two green color board. One is without components and one is assembled PCB which has the components on top of that. So once after we get the PCBA, some hardware based testing, then we will integrate the software, then the complete functional testing will happen. This is just a sample block diagram. Suppose if you are building using a microcontroller, so we will have some peripherals also, IOs also. IOs means input output. So here you can see touch. It can be a touch button or sensor which use as a input, and maybe we can give output on an LCD or any LED indication, or the controller, we can keep a RAM or flash, RAM or ROM. So this all depends on the application. What all we want to give as a feature in the application, that we will give it in the block diagram. So this is just a sample block diagram, which you also can use if you are going to build any circuit. So a block diagram, a basic is this one. So since I have mentioned on this RAM and flash, I will just give an overview of the memory technologies in the current market. So semiconductor memory technologies can be divided into two, ROM and RAM. So what is a RAM? RAM is a form of data storage that can be accessed randomly at any time in any order and from any physical location. Then ROM, a form of data storage that cannot be easily altered or reprogrammed. So what is the usage of this? Why we need this random access, and why in some case we need only read only? Because RAM read data quickly to run application. It allows reading and writing. ROM stores the program required to initially boot the computer. It only allows reading. So suppose if we take an example of a computer and music player. So computer needs that initial booting program that will be accessed only once when we start the computer. So in that application of computer, we are using ROM there to store the boot program. And for the music player, we need the access read and write. Whenever we change that music, we need that to play. So in that case, we are using RAM memory there. Next, we'll see the volatility. RAM is volatile. Contents are volatile means contents are lost when the device is powered off. And in case of ROM, this is non-volatile because the content should not be erased when the system is powered off, because next time when you turn on the computer, if the boot program is not available, then the system will not start. So in RAM, we can have static and dynamic RAM, and in ROM, flash is the EEPROM is the EEPROM is the. Next is the power supply design. So we have created our block diagram. So how much power is required for this circuit? That we need to calculate. So here I have just taken an example. A circuit which consists of 6 buffer, then 1 microcontroller unit, SD card, then DAC, then oscillator, then LPF, then LEDs and passive. So you can see like a branch with a regulator and source in the front. Since the circuit is giving out in branches, we call this figure called power tree. So whenever we do a power supply design, first thing is we need to draw a power tree like this based on our application. So in next slide, I will show you how to actually calculate that. So you can see that right hand table, function or type, LDO part number is mentioned. So for each component what we are selecting, there will be a part number associated with it. Why? Because every manufacturer will have their own components. So how to identify this between the manufacturer? Because they will define the part numbers. So LDO 3.3 volt. LDO is nothing but a regulator. 3.3 volt regulator we can get either from Texas Instrument or from NXP or from any other manufacturer. So we are and one manufacturer datasheet will not be compatible with the other manufacturer part. So always make sure you are selecting the right datasheet when the component is taken. So here I have mentioned the part number of that particular part. LDO TC1262 is the part number, and the quantity which we are using is just 1. And the nominal current is mentioned over there. Similarly, for the other buffer, MCU, SD card, DAC, oscillator, LPF, then LEDs and other passives also consume some sort of current. So, for example, I'm taking LED and passive. One quantity only is used, and the typical current which is consumed by this LED is 0.0047. So that particular, the last branch is taking 0.0047 current. Just above that, LPF. LPF branch is consuming total 0.0046 ampere. But single LPF is consuming 0.0023. So always with the number of components you are using for the total current consumption. So for likewise 1, 2, 3, 4, 5. For the 7 branches, you need to calculate the current based on the current consumption of each part. Then we are adding up all this current to get the total current consumed by this circuit. So the total current will be just above that top table I have mentioned 0.313621 ampere. That is the total current consumed by this circuit, or that is the total current you need to provide to circuit for that circuit should be functional. What happens if you are giving less current? If you are giving less current, only few of these components will work. Like MCU, like the microcontroller unit, if you are not giving enough current, it will not turn on itself. So always make sure you are providing adequate current from this regulator. Then you know the battery voltage. So now you can calculate the total power consumed by this circuit, which is using the equation power equal to VI. So that is the total power consumed by this particular circuit. So always start with a block diagram for your particular circuit, then goes for power calculation. So this is very important step to calculate the power and know how much current is getting consumed, because during a PCB design you have to give this information to a layout engineer. Based on that, he will determine the PCB traces or track width. So for a 1 ampere signal and a 10 ampere power signal, it's not the same PCB trace. Just keep that point in mind. So we have seen this block diagram as well as power tree. Next, we'll see how to start a schematics. So first step in schematic is the select the components you will be using. So once you have the list, collect all the data sheet and look at the suggested application circuits in those data sheets. So for most of the components, they will give one application circuit. Application circuit means you can use that particular component in circuits like that. So that will be a guidance for us to start with. So when I say about components, we can categorize into two. One is active, the other one is passive. The devices or components which require external source to their operation are called active components. Suppose we take the example of a diode. So diode requires an external source for its operation. So if we connect the diode in a circuit and then connect the circuit to supply voltage, diode will not conduct until the supply voltage reaches to 0.3 in case of germanium or 0.7 volt in case of silicon. So that is the major difference. So passive components which do not require external source to their operation is called passive component. For example, resistor, capacitor, inductor, etc. So next is you might have seen this through hole or leaded components. But in the industry, we generally use SMT packages. SMT is nothing but a surface mounted component. So here I have on the left hand side, I have shown some components. So basically in PCB, we will see very small components like this, and you might think how we are actually differentiating between these because all look similar. So suppose example, there is a green color chip fuse, then black color chip resistor, brown color chip capacitor. You can see even though the leads are of the same color, the center marking is different. So always for a resistor, black color port will be there. For a capacitor, brown color will be there. And for fuse, green will be there. And for the remaining other things also varies as per standard. So you can see on to the right hand bottom side, it's a assembled PCB. And some markings are there like R128, C88. So why we give this numbers or naming is onto a circuit when the PCB we get, we should know which resistor and in which location it is. So always we will mark the components with a reference designator. And there you can see so many brown color tiny items. Those are capacitors. And the black ones, the tiny black ones are of resistors. And you can just see about that R. R means for resistor and C for capacitor. Similarly, for the IC transistor, we use different terminologies in the industry. And towards the right top, you can see that components of different sizes. So one is of very tiny component accessed in the market 008, 004, and just on top of that you can see 01, 005. These are all naming for their dimension. And next to that 0201. So what does this actually mean? 0201, 0402. So 0402 is nothing but 0.04 length into or by 0.02 width inch. Termed inch dimension. And 0603 and the bigger one is 0805. Even bigger than that is the 1206, 1210 that I have not shown here. So you can see this component is sitting on two pads. You can see two silver color squares are there. On top of that, the component is sitting. That two silver color pads we will be giving in the layout file. That is called as a footprint. So always footprint is the land pattern for that particular component. So we will give the footprint name as in case of capacitor or resistor, it can be like this 0805, 0603. And for ICs, it will be different. So each component have a different land pattern or the place to sit on a PCB. So next is, I have told about schematic. For each component, we need to create a symbol of component in the library. So the first step to start with the schematic, we need to create a symbol for that. So here I have taken an example of a right hand side bottom. You can see that ST, that is a screenshot of data sheet. So when you open a data sheet, it will come up like this. And inside the data sheet, you can see the pin functionality on the pin types, variants, and you can also see the footprint of the particular component. So, excuse me. So the black color one is the physical component, what we actually see. Next to that, there is a block I have given, that is the logical representation of this particular IC, which we will be using in the schematic. So next to that, you can see some leaded orange color one. That is the footprint which we will be using for the layout. So on top of this footprint, when we get the IC or component, on top of that, the IC will sit. So this is a sample for the schematic. To create a schematic, first we need the, I said, the symbols are required, which we build in a library. And we need to place the symbols in a schematic page. So you can see one MCU here, then on the left hand side, one connector is there, then some capacitors and crystal oscillators are there. After placing all these components, we will start wiring this. Just take the wire tool and connect between each. So in schematic, the terminology for wires is nets. We will call each wire or signal, we call that as a net. So once the schematic is completed, we will check for the DRC. Design rule check will be there. It consists of logical and other errors. It is an automated tool. Once the DRC is cleared, we will generate a net list. That means the signal list. This net list will be imported onto layout. So next is, we'll see, okay, this is, these are some screenshots for the schematic, how to place a part and how to drop between the wires. In case if time is there, I will try to show in actual tool. Okay, so when I talk about layout, it is equally important to show you a capacitor. So these both are capacitor. Axial through hole is one type of capacitor. SMD version is a surface mount capacitor. Through hole connection means that small wires known as leads are fed through holes, which we generally use with the breadboard. So each lead will be soldered onto the PCB. So surface mount PCB don't use this wires, but instead many small leads are soldered directly onto the board, meaning that board itself is used as a wiring surface for different components. So we generally use SMD version of components because it uses less space also. So the other remaining space we can utilize for this PCB track, usually for the high speed and other purpose. So we generally prefer assembly version of components uh, for the ease in soldering as well as the uh, space constraint point of view. So next is on the left hand side, I have shown you a footprint of the capacitor. So you remember the footprint is the land pattern for that particular component. So while we start a layout, first thing is to, similar to the symbol what we created in the schematic, we need to create a footprint in the layout also. Next is we place the component in a layout or board file. First step is placement. After the placement of all components are completed, we will start routing. Routing means to draw the trace from one component to another. So while drawing this trace, the trace width matters there. The trace spacing matters there, because if two traces are so close to each other, there can happen coupling effect, which I told earlier. The EMI interference can happen, or the crosstalk, mainly the crosstalk can happen. So always there will be a set of guidelines which the layout engineer should follow, so that there is no interference between the different traces. And the bottom picture. So always in PCB, when you see a PCB, it will have so many lines on top. But what happens if the space is not enough for all the signals to lay on that particular PCB? There comes the layer concept. So when you see a PCB, it's not always on the top. There is inside also layer is there. In that layer also we will have signal or power, and layers can be 2, 4, 6, 8, and it can reach 40 also. So many thousands and 10,000s of nets you can actually accommodate onto a PCB using this layer concept. But on top and bottom layer only, we will assemble the components. Inner layer we generally don't assemble, but there are some components like that, but the manufacturing cost will be more for that. So trace on top layer you can see, and inner layer also you can see the signal. So we define the number of PCB layers upon how complex the circuit is. So as I said earlier, PCB can be a 2-layer layer, etc. And there can be single-sided. Single-sided means just on top only we are mounting the components, or it can be double-sided PCB also. On top and bottom we can mount the components. So all the layers which I told earlier, all layers are interconnected with copper-plated holes. So a general multi-layer printed circuit board has following layer stack. So top, you can see top layer and bottom layer. There we are mounting the electronic components, and inner layer 1, 2, 3, and it can extend also, that we are using for routing purpose. So all the active and passive components are assembled on top and bottom layer. Then inner stack layers are meant for routing only. Both through hole as well as the surface mount component can be soldered on either side of the PCB. So PCB is nothing but printed circuit board. So PCBs are most commonly made out of fiberglass, composite epoxy, or another composite material. So what is actually inside these layers? So first picture, there is a substrate. There is on top of that a copper layer which is shown in orange color, and a solder mask. A single layer or single-sided PCB is one that is made out of a single layer of base material or substrate. So there will be base material. So one side of base material is coated with a thin layer of metal. Now, on that layer only all our signals will be there. Copper is the most common coating due to how well it functions as an electrical conductor. So once the copper base plating is applied, a protective solder mask is usually applied, followed by the silk screen to mark out all the elements on the board. So if you remember, I have showed one PCB earlier which has some markings on top, R128, C88, to identify the components. So those are we call it as a silk screen marking, which will normally be in white color to identify the component. Next, a double layer or double-sided PCB have base material with a thin layer of conducting metal like copper applied on both sides of the board. Then you can see not only assembly, we can do through hole also. So for the through hole, holes will be drilled through the board and allow circuits on one side of the board to connect to the circuit on the other side. Suppose if a capacitor want to communicate, or top side assembled capacitor want to connect to the bottom side some signal. So we just drill a hole through the PCB, and that drill hole is called a wire. Through wire, signal can pass and reach the top or bottom. So that's how the PCB's layers are getting interconnected. Then solder mask. Solder mask is actually a thin layer of polymer that is put on a circuit board to protect the copper from oxidation and shorts during operation. So that particular layer, solder mask, also protects the PCB from environmental influences such as dust or other contaminants that may lead to shorts in the long run. Next, explaining down to the PCB substrate, that is a physical material that holds the traces and component. So PCB substrate is basically a dielectric material to which a copper layer is attached. So either on one side or both the side. So substrate material defines the board's rigidity and flexibility, as well as the other electrical properties such as board impedance. So everything should be controlled. Next is about Gerber. So once the layout is completed, layout file, all layers defined, all layers routed. Once the circuit is completely routed, we will generate a file called Gerber. So here in this screenshot, I try to capture the entire Gerber view. So here you can see some area red color, some are in yellow, blue. So that each corresponds to different layer. Like some are the assembly layer, some are the inner layer, some are the silk screen layer. So each color corresponds to different layers. So the industry standard file format for PCB fabrication is called Gerber file. So this Gerber file tells the machine in PCB production in process on how to draw patterns, make traces, drill holes, and cut the board. So in Gerber, we actually define the PCB dimension and the drill holes on what size we need, then trace width also what size, and the material, the number of layers, everything will be covered in the Gerber. The PCB fabricator will take this file as input for their fabrication and will directly fabricate the PCB as per the design what we have done. So next is PCB-A, assembled PCB. So here at our Velankani, we have a facility of in-house facility, which is over 6,000 square meter. And we have a fully automated machine assembly. I will try to play this video. In case if the video is stuck or anything, just tell me. So I hope you all got a virtual visit of our factory.
Yes, ma'am.
So next is about the validation stages. So till now I have explained the schematic layout, this PCB, then it came till assembled PCB. So right after this assembled PCB, we will not directly go for a mass production. Before mass production, there are certain stages. So in validation testing stage, we have EVT, DVT, PVT. After PVT only, it goes for NP, that is mass production. So we'll see what is EVT. EVT is nothing but a engineering validation. So in engineering validation, we ensure functional requirements are within the spec. Spec is nothing but a specification. So basically, why we do this engineering validation test is we want to weed out any hardware failure. So normally, once after the concept everything is defined, once the proto is done, we will build some 20 to 50 unit of this PCBs along with the mechanical everything. So that comes in engineering validation stage. Next is DVT. DVT is nothing but design validation stage. So once the design everything is completed and finalized, next is for the factory process. So factory also need to do certain kind of process and fine tuning for that machines to assemble the components and PCB finally, so that it will be error free process. Otherwise, if we skip these stages and if we directly go to mass production, there are chances that process is not defined, so there comes soldering issues on the PCB or some functionality failure, anything can happen. So we always stick to these stages. So for the DVT stage, some 50 to 200 units we will produce using a proper production process, and during this stage we will do the stress test also. So we will give some stress condition to the PCB and see if it is passing that or not. Then comes the PVT stage, pilot validation stage. This is similar to a official production run. Unit has to pass all the tests proving that it is suitable to sell. Then, in case if any adjustment are required for the tools and process, then it can be made during this stage. So in that picture, you can see EVT, DVT, and PVT, but this does not involve PCB. This is just to show for the mechanical casing. So during the EVT stage, we are doing the mechanical enclosure with a 3D printing. Why? Because we are not using any mold in this, because we want to see if any defect is there, if any functional failure is there, because if we already created one mold, that cost will be higher, and we do not need such a high cost to be spent on during the proto or sample stage. The functionality we are doing it with 3D printing. The next DBT stage, we need some more finer measurements and everything. So we are using a silicon molded enclosure. Once it passes silicon molder, silicon mold, if all dimensions are fine, then we will go for the actual mold, and the production will be on the actual mold. Next, I have one more video of PCB fabrication, but it is over somewhat 20 to 25 minutes. So I have just added that in the presentation. While I share this presentation, you people can see I'm not playing that right now. So if any questions are there, I am open to that.
Participants, any questions? Ma'am, there is a question in chat box. Any internship activities for the students?
Sorry?
Any internship activities for the students?
Oh yes, so we are open to that. We can couple of investment already are here. So in case anyone is interested, you can send me your resume and get opportunity.
Okay, ma'am. I think it was being asked by Siddesha, sir.
Oh, okay. Sir, hope I'm able to answer. If you need any further details, please drop me an email.
And there is one more question, ma'am, in the chat box.
Mhm.
I think you were showing about layout. There was a
Yes.
question from madam that which tool is that?
Layout in the found in the same country, we are using Metal Graphics and Allegro. So we have layers in both. Any other question?
Participants, any questions or any queries?
Hi, ma'am. I am Nishni. Actually, I want to know when designing a double layer boards. Sometimes instead of using ground trays, we try to use ground pour. Which one is more effective, like using ground pour or ground trays?
Okay. So that depends on the your the layers. Suppose if you are using a two-layer board, dedicating a ground pour to that particular two-layer board, it will be difficult because you will have components on top, maybe components on the bottom side also. So what happens here is in case you are not able to give that ground pour due to space constraint, just near to the signal, we will give ground guarding trace. Like a signal will be moving just near to that on both the side, we will give a ground trace. So basically, we prefer to pour a ground, then the return current can pass through easily. So in case space constraint is there is no issue at all. We always give a ground trace as a guard for the signals. Otherwise, you need to, in case of high-speed signal, if your circuit high-speed signals are there, then we need to increase the number of layers and give a proper ground or power plane for the return current to pass. Is that answer convincing, or you need more details?
In four-layer board also, if the top and bottom, if you're giving signal plus ground, like this ground pour or polygon pour, will that be more efficient in case of interference reduction and all, or keeping separate ground plane and keeping only signal layer on top and bottom will be better?
Okay, so when you have an option for more than two layers, always route signal on one layer and keep a reference plane for this ground, because onto this reference plane all of your noise and return current will come. So when you try to accommodate your return current, suppose if you are using a signal layer on top, and next also if it is a signal layer, there is high chance of crosstalk. So that is not at all recommended. So one signal layer, just beneath that reference layer should be there, and again another reference layer, and then comes the signal layer. That is the typical PCB stack-up which is recommended. Is that clear?
Okay, ma'am.
Thank you. Any other
Any more questions? I think no. So we have come to the end of the session. I would like to thank Ms. Minimol ma'am for taking out time from her busy schedule and sharing with us in-depth knowledge of working and design of various electronic circuits and touching upon the different types of semiconductor memory then touching upon the power supply design and its calculation, different types of PCB layers and the design of the PCB, and validation stages in a nutshell. Thank you, ma'am, for sharing your knowledge with us. Thank you so
Well,
much.
thank you everyone for attending this session. In case of any question or anything is required, keep dropping an mail. Anyway, I will share this presentation, and for the videos which I was not able to show in that, you can always see in this presentation. Thank you everyone.
Thank you, ma'am. Thank you so much. Dear participants, we'll break for 15 minutes. We'll rejoin back by 11:40. Thank you all. We'll start our next